Good morning, and thank you for joining us here at Son Tek for our webinar entitled Taking the Mystery Out of Measuring Waves, Tides, and Currents. Presenting this morning are Oceanography Applications Specialist David Velasco and Senior Software Engineer Matthew Hall. And now let's begin our presentation.
Hello everyone, and welcome to another live broadcast in our ongoing webinar series. On behalf of myself and my co-presenter, I'd like just to say that we're very excited to be here. We realize that there are quite a number of different techniques available today for the measurement of waves, tides, and currents, and many of these can be complicated and difficult to set up and to analyze, especially wave data. Now, we here at Son Tek believe that collecting good quality data should not be reserved just to the high-end researchers, but that any should be available to anyone who wants to or needs this type of data. So we hope that this webinar will help answer some of your questions concerning the measurement of waves, tides, and currents. Let's just begin by introducing ourselves. My name is David Velasco, and I'm an Oceanographic Applications Specialist here at Son Tek, where I have been for about 5 years now. I started at Son Tek in the technical and application support side, so I've been exposed to a lot of these questions and on a variety of different topics. So I believe that the motivation for this webinar really came from that experience. It was really clear to me that it was a huge need out there for a simple discussion on some of the topics that we're going to be covering today. And with this, I would like to introduce my my co-presenter, Mr. Matthew Hull.
Hello everyone, my name is Matthew Hull and I'm a senior engineer here at Son Tek. I've worked on various software packages for Son Tek over the years. Prior to coming to Son Tek, I worked in coastal engineering, and I hope to utilize that experience in making things simpler and easier in the measurement of waves, tides, and currents.
Okay, let's continue. Well, Son Tek, for those who probably know, is located in sunny San Diego, California. And the picture here shows our brand new facility that we inaugurated earlier this year. It is in this facility that we manufacture, test, and quality control all of our instruments. I know the very nice, wonderful Southern California weather makes life in San Diego very enjoyable, but it's not the main reason why Son Tek is here in San Diego. In fact, actually, San Diego is widely recognized as being the birthplace of commercial Doppler technology. Almost every advance in commercial Doppler products and their companies have some sort of connection to San Diego in one way or another. Just as an overview here of our presentation, just wanted to show some of the topics that we're going to be talking about today. We'll first begin by giving a brief introduction to Son Tek, our technology, and some of the applications that we make and that we act in. We're also going to talk about some of the wave fundamentals. I know why measure waves and how to measure waves. And we're also going to talk about how Son Tek's Triton-ADV system makes it easier for people to get the information that they need. And of course, we'll finish by opening up the line to your questions. However, feel free to type in your question at any time that you like, and it will be sent over onto us. Okay, so where does Son Tek fit? Well, Son Tek has been manufacturing oceanographic products since the early 90s. We serve a very wide range of different type of applications. As an example, from the photo here, you can see two of our ADPs set up back to back and being used for long-term monitoring of deep ocean currents. Here you can see in this picture one of our rugged ADV ocean systems being used from some wave studies. I believe actually this is down here in Southern California where this picture was taken. Another great image here of how our ADVs have also faced many waves over the course of their lifespan. You can see from this photo here, just taken just north of Scripps Pier here in San Diego. And of course, we're also present in many ports and harbor applications, especially with our side-looking profiler systems that are very widely used for the measurement of current speed and direction for vessel traffic management. And last but not least, of course, we also offer a number of different instruments for the folks who are working in estuarine regions as well. So the question now, of course, is why do we measure waves? What is it about waves that makes them so important? And why is it that people are out there measuring waves? Well, the mere fact that you yourself are attending this webinar today is evidence that there is a very large demand for wave measurement. But why is it that we measured? Well, waves are a key mechanism in understanding coastal sediment erosion and transport, the design and stability of coastal structures such as breakwaters and jetties, and in determining the geometry of beaches, to name just a few of the different applications. So as you can see here from the slide, the knowledge of wave height, period, direction, and other wave parameters are very critical to just about any process that goes on a coastal zone. So now that we have a general understanding of how important wave information really is, why has it been such a complicated thing? Well, certainly in the short time that we have here together, I cannot do justice to any of the to a very in-depth discussion on waves. But let's just go over some of the key topics. What is a wave? A wave in the ocean is a disturbance of the water surface that is propagating in space and in time. In the simplest form, an ocean wave can be described by a cosine function, which is illustrated here in this slide. And this is what we commonly call a regular wave. Here we have simplified, here of course in the slide we have simplified the wave into just a two-dimensional form that is varying only in space and in height and in time. And so in other words, the wave is just moving up and down with time in a sinusoidal fashion. We have also made a very large number of assumptions concerning things such as boundary conditions, wave kinematics, and wave dynamics that are just simply beyond the scope of this presentation today, but that researchers have spent essentially a lifetime on studying. In any case, just by judging from the image here on the screen, it would seem reasonable. It seems reasonable that it to be a simple thing to track just this up and down movement of the water surface over time, right? Well, yes and no. As it turns out, the ocean surface does not move up and down in a nice sinusoidal fashion as the last slide. Anyone who has stood on a beach and looked onto the water surface can attest to this fact. But in reality, the sea surface moves around in a very complex way that almost defies description. And this is what we call an irregular wave. In the ocean, what we really have are many different types of waves that are actually superimposed on another. Here in this slide, we try to capture some of this complex movement, and just to show that the elevation of the sea surface above the bottom over several minutes here. So here we have a course over about 2,000 seconds here, where we have the surface of the ocean being tracked over the course of this time. Just on the bottom here, I have zoomed on the first couple hundred seconds of this record, just for a better viewing. Now, just keep in mind that we're still only looking at a two-dimensional representation of a wave record. And here we're not even considering direction. So even this looks a pretty complex signal. It actually looks much more complex than that in real life. For example, to add another level of complexity on top of all of this, most of the characteristics of a wave actually will change with as the wave propagates from the deeper ocean into the transition and into the shallow zone, all the way into a crashing wave on the beach. So why did wave measurement have to be so complicated? Well, in addition to all of the things that we have already discussed, namely the complexity of the surface of the wave, keep in mind that what it is that we're in a physically challenging environment to deploy any kind of instrument. We have waves crashing, we have rough conditions at sea, so it makes it just for a physically difficult place to work. So in order to properly measure waves and to be able to survive the waves themselves, instruments over the years have to have a few very key characteristics. Well, one is that they must be physically robust. In other words, be physically strong enough to survive the environment. They also must be able to sample their sensors fast enough. This typically means 1 to 2 times a second in general. They must also accurately measure the key parameters, such as currents and pressure. And therefore, original wave instrumentations ended up being very expensive, difficult to use, and physically large in size. There are a few tips I just wanted to share, just from experience on deploying some of these instruments in the ocean. The most obvious one is make sure before you put something in the water that you're marking where it is that the system is deployed. As if you have to come back a few months later, you know how to find that system. A lost system does no good if you cannot get the data out of it, of course. Obviously, you want to have a proper mount for your instrument. Things, for example, such as the weight of the mount need to be considered to make sure that they will survive the expected currents. Also, the design needs to make sure that, for example, if you're in an area of high trawling or where fishermen are dragging nets on the bottom, you need to make sure that the mount is designed in such a way that it will not get caught should a net go over the mount. And obviously, the system itself, the frame itself that you put the system in, you got to make sure that does not affect the instrument's performance. So really, the bottom line was that all that we just discussed was the motivation in Son Tek creating the Triton-ADV system as an alternative for the common wave gauge. The Triton is very simple to set up and use, but yet still provides a wealth of information. The background image here shown in this slide just depicts some of the typical environments where the Triton-ADV can be deployed. The target installation depth for this system is in the 10 to 20 meter range, but with some limitations, deeper installations can also be performed. So as the system's name suggests, the Triton-ADV was built around the renowned ADV platform that was developed here at Son Tek. The ADV affords a high accuracy, single point, three-dimensional velocity measurement for the Triton-ADV. Now, really, the unsung hero of the system really is the Son Tek exclusive auto-velocity processing. What auto-velocity does is that it allows the system to handle a wide range of flow conditions without causing the data to wrap. As illustrated on the diagram I have here shown on the screen, systems without auto-velocity cannot automatically compensate for change in flow conditions, and this results in incorrect velocity values to be recorded whenever the flow goes above the user preset range, which is shown here illustrated on the green line on the slide. Now, the Triton-ADV, however, automatically adjusts its configuration throughout the deployment, preventing the recording of bad data. Auto-velocity allows the Triton to measure velocities in the range of plus or minus 4.5 meters per second, all without compromising data resolution and without complicated configuration options, which is not, which is very, it's an exclusive thing about the Triton-ADV, because typically these preset velocity ranges do infer some loss in the resolution of the system. As we'll discuss soon, the Triton uses the PUV method to measure directional waves. Now, the PUV method has been widely accepted and is a proven technique for measuring directional waves. We'll discuss it a little bit further in detail later on the presentation. Another very interesting feature of the Triton-ADV is that it can operate as an acoustic altimeter when installed, obviously, in a down-looking setup, as illustrated here in this image. The system will record a time series of the distance between the sensor itself and the bottom that can be used for sediment erosion, transport, or accretion. Another nice feature of the Triton, as you can see from this image, that is a very compact and lightweight system. The entire system is shown here on the screen, and it's only 70 centimeters long. It's only about 10 centimeters in diameter, and it only weighs in air 3.2 kilograms. So it's very lightweight and ready to deploy. And of course, to top the list, it's a very affordable system. The cost for a Triton-ADV is about 50% less than what a similar acoustic Doppler profiler goes for, which leaves you a little extra cash to buy some other instruments.
Okay, I'd like to spend a little bit of time talking about how we actually engineered and designed the Triton-ADV. We mentioned earlier how wave measurement platforms were very expensive, very difficult to use, and very large in size. So what we aimed to do was to remove some of these obstacles and integrate all the different components into one single platform. And the single platform you see in front of you, right? Everything from the acoustic transducers to the batteries are enclosed in this ready-to-use field housing. All data is then tied together in a single data stream and recorded in the onboard data logger. Now, despite this being a very powerful platform, the Triton-ADV's small battery pack permits deployment lengths typically around 1 to 3 months. However, if you use one of the external battery packs, you can typically extend this deployment up to approximately about 3 times the duration.
Thank you, Matthew. Now let's just go a little bit more deeper in detail to the PUV-Wave Measurement technique. Just to talk about how some of these directional waves are actually obtained by the system. Although it is common to say that a given system actually measures the wave, we actually want to just make sure that what we're doing here is that we're inferring waves from other parameters such as velocity and pressure. So unless the system is actually tracking the ocean surface, like you typically do, like with a capacitance rod or something, or a buoy right on the surface itself, in reality what is being done is that the waves and statistics are being inferred or computed from one or more measured parameters. And of course, one of these methods is called the PUV method. Again, as we discussed, waves are a disturbance of the surface of the ocean, and they travel in time and space. And as they travel or propagate throughout the ocean, the displacement that they cause on the surface is felt not only at the surface itself or just below the surface, but also at depth. Now, data from a high accuracy pressure sensor records this change in the pressure, which is what is shown here in the P here in the slide. Now, of course, the waves are also propagating, and as the waves propagate, that means that they also have a velocity, and this is where the ADV portion of the Triton actually comes into place. The horizontal components of this velocity field, that is the U component and the V component, typically the longshore and crossshore components, they are measured by the Triton's velocity sensors. In the PUV method, both the pressure and the horizontal velocity components are measured at the same time, so that is that they're synchronized together. And this is where the term PUV comes into place. Now this slide here shows just a small sample of raw PUV data, in this case here collected by a Triton-ADV system just off of San Diego local beach here. And as you can see from the slide here on the graph, on the pressure graph, it shows that it was deployed in about 6 meters of water, more or less. The green line shown here on the top graph displays the raw pressure data. From this data, it is from this pressure data that wave height and period statistics are computed. Now the bottom graph shows the two horizontal velocity components of the water motion. The Triton-ADV uses these two velocity components to compute the direction that the waves are coming from. So you have here the red representing the U and the blue representing the V components. Now when these three parameters are combined, that is the pressure value recorded at a fast enough rate and over a course of a given time, typically in the range of 15 to 20 minutes, when they are combined with the velocity data, these are what we use to compute the wave height, period, and direction statistics for the wave record. Here on this slide over here, this is where we show just some graphical results that you can get from a system like the Triton-ADV. This is directly out of our analysis software. This graph shows wave direction and period statistics displayed on a polar plot. For those who are unfamiliar, polar plot is commonly used because it just gives a clear indication of the wave direction distribution. You know, you can look at a graph such as a polar, that when it's plotted in polar coordinates, and just from a quick glance at the plot, you can easily see that most of the wave energy is coming here, in this case, from the east. Now, something else that a polar plot clearly shows, and it's shown here in this example, is the bimodal distribution of the wave field. Most of the wave energy is concentrated around a frequency that corresponds to a period of about 6 seconds, which is shown here in the slide. But some of the energy, however, you can see is at a lower period of about 13 seconds. Now, this, for example, can be interpreted as being a higher energy local C mixed in with just a low energy swell. This is a similar graph from the previous one, is just now we're looking over the course of time, whereas the last slide would just look at one specific burst of data. Now we're looking at the same deployment but over the course of time. This here you can clearly see also the bimodal distribution that can be observed here by two separate well-defined areas existing over time. One is sort of the thinner area closer to the bottom of the graph, and the other is the thicker area towards the sort of the bottom third of the graph there. Now this is just a simple example of a direct output from our software. So how do we get all of this information? Well, again, this is the part where I probably tell you just, spend a couple years studying wave mechanics to be able to figure out all the details of the answer. But just a couple of the key points here is that one of the things that we use is what we commonly call FFT, or a fast Fourier transform. Now, what an FFT is just a mathematical tool that is used to decompose a very complex time series record into its base components. This is a tool that is widely used all over the world and is very accepted today, and it's be used for a number of analysis of complex signals, from anything from sound recordings of popular music all the way to earthquake analysis you can use FFTs for. And of course we also use spectral analysis, which is another tool that we use to separate the different frequencies that make up this complex signal. Now, the PUV method is a pressure-based method, meaning that we're basing it on data from a pressure sensor. Now, the pressure signal, well, in addition to the velocities for direction, of course. Now, the pressure signal generated by the passing wave attenuates with depth. This is common knowledge and can be fairly easy modeled. Now, this means that the pressure-based sensor that is mounted on the bottom will have a trade-off between the installation depth and the minimal detectable wave period. The table here on the slide on the right side shows just a rough estimate of the minimal detectable period for just a 1 meter high wave at different depths. So as you can see, the deeper the installation depth, the longer the wave that will be limited for the system to measure. For example, if you look at an installation depth of 20 meters, you will typically capture waves with periods of at least 4 seconds. Should you like to capture waves of higher frequency, meaning shorter periods, that means that the system will need to be installed in shallower depths. So the trade-off is the shallower the depth, the shorter the period. I would like now to, we're going to just talk now about the software that we have written to simplify all of these processes. We talked about how the waves are measured, but now we need to make sure, well, how do I actually set up an instrument to measure the waves? And I'd like to pass on now to our senior engineer, Matthew Hull, to talk about our software a little bit.
Okay, what you see in front of you is the deployment software that we have for the Triton-ADV. What we've done here is we've tried to focus on making it as simple and easy and get you deploying the system as quickly as possible with the least amount of fuss. So we've simplified a lot of the things. All of the advanced features are still there and they're still accessible, but if you want to get out there and quickly deploy an instrument in maybe a couple of minutes or even less, it's quick and easy to do that. So when you first start up the software, you've got two options. One is connect directly to a live system. The second option is to plan a deployment. And what that means is that you can sit in the office and you can actually set up a system the way that you want to have it deployed, and then when you go out in the field, you just load that template and you're ready to go. Once you connect to a system, you get a quick description of all of the hardware settings for the system, the recorder, pressure sensor, everything else. So you can see exactly what the serial number is, and you get a quick overview of the actual system you're connected to. The first step when you're actually doing a deployment is to enter the information on how you have the system mounted. So what we typically need is the height of the system above the bottom. Now that's not the height to the top of the ADV, but actually the height to the top of the housing. Now you can set up an ADV, a Triton-ADV to be looking upwards or downwards, and the deployment software will cater for all of those sorts of options.
Just wanted to add one thing here to Matthew's discussion, is that the reason we're looking for the system's height above the bottom is that, as we had discussed, the waves are going to attenuate with depth. So in order for us to properly compensate for this attenuation, we need to know where in the water column we are located.
You can also see that down the bottom of the screen there are a series of little steps, starting with Start Here, System Settings, Deployment Conditions, and so on. Right now we're on the Deployment Conditions page. You can see how that's been highlighted. Using that little control down the bottom, that allows you to quickly jump backwards and forwards between pages if you want to just check, or if you need to review certain settings that you may have set. Let's continue on to the next page. Okay, here we go to actually setting up the system for how you're going to collect data. How often you're going to collect data, whether you're going to collect wave data, how you're going to collect your velocity data. Now this may seem very complicated, but it's actually very simple and easy to set up. So let's start from the top. At the top we're looking at the velocity and the wave measurement. So the first question is, how often do you want to collect data? So what we've done here is, you just click on that little combo box and it gives you all the options for how often you want to collect the velocity data. So we've selected in this example to collect velocity data once every hour. Second question is, do you want to measure waves? The answer is yes or no. Now typically we've had in the past people have a lot of trouble working out exactly what are the best settings that they want to use when they actually collect wave data. So what we've done is we've simplified the whole process, and we've set the optimum parameters for setting up for collecting waves. Now, if you would like to set up the system to collect waves in your own way, those options are still available, and they're at the bottom of the screen under the advanced settings. So you still have that freedom and flexibility to select those sorts of options if you need them. But if you want to quickly get out there and deploy it and know that it's going to be working for collecting waves in a very standard and operational fashion, then it's very quick and easy to do. Below those two settings, you can see a graph, and what it's showing is blue and green little bars. The blue bars are the duration of the velocity measurement. The green bars are how long the wave measurement is. So you can see here that we're collecting data once an hour, so between the 0 and 2 we have 2 blue measurements for the velocity and a corresponding wave measurement with every velocity measurement. Below that we have 2 boxes, one for the power management and one for the recorder. These allow you to see how much time you can have the system deployed for. In this particular case, we have the battery set for about 19 days it will last based on this deployment, and the recorder is obviously sufficient to last that particular duration. So based on that, this deployment is limited by the battery power. Let's continue on to the next slide. If you choose that you would like to have that little bit of extra control in how you set up the waves, you can click on that advanced settings button and you pop into this little dialog box here. On this screen we can do all of the advanced settings. You can set it up exactly the way you want. You can adjust velocity ranges, the timing, and how you set up the waves. Now this is only if you really want to mess around with those settings, but for the most part just turning the waves on using the standard settings on the previous screen is good enough. If you click on the next button, we can go to the scheduling page. This is very simple and easy to set up. Do you want to start the deployment now, or do you want to start it in the future? So if you're actually out and you're about to drop the system over the side of the boat, or however you're going to deploy it, you would say typically yes, I'm going to start it now. However, if you've set up the system in the office and you've got a long drive to get out to the site, then you may want to set it in the future. Easy to select the date and time of when you want to actually start the measurement, a file name, and comments. Now, in the comments field, I know a lot of people have a tendency to like to leave them blank, but we always recommend that you add in just a couple of lines on the actual deployment conditions and any sort of weather conditions or any other information that you would use to identify this particular deployment. Now, a lot of people leave them blank. We always recommend that you add in just that little bit of extra information and take that little bit of extra time to do that. Last of all, when you click on the next page, on the next button, it jumps you to the summary page. Now the summary page gives you a written description, not all of these little boxes showing you a lot of numbers which you have a tendency to ignore, but it's a written description that you can quickly and easily read and see if the system is set up the way that you need it to be set up. You can print this page, and we always recommend that you do that, so that you have a log of exactly how the system was set up, so that when you go back later you can see how it was set up, and then you can use it as a reference. You can say, once you've set up a system in a particular way, you can save these settings as a template, which then you can use if you are, for example, deploying multiple Tritons in exactly the same way. So if you had, say, for example, 4 Tritons, all needed to be deployed in exactly the same way, you just set up one template for one, and then for the next 3, load that template and just save it and just transfer those settings to the system. So it's nice, quick and easy. The next 3 systems you can do in a matter of seconds.
We actually had a question from Tom. I'm not sure where he's located, but Tom has asked whether the system has an internal clock, and if so, is this time automatically synced with the software while doing the scheduling? And the answer to that is yes. I would like to just go back to one of the previous slides we had shown here, and because of the limitations with the actual webinar, we cannot do an actual live showing of the software itself, so we actually have to have a template that is being used here for just the illustration purposes. But should you had been connected to an actual system while setting up this deployment, rather than just working off a template as we have here, on this part on the top right hand side of the screen, you would have shown, which is right over here, you would have seen an entire new set of tools appear. And what those tools will do is that they would automatically check the computer's time, and it would will also check the Triton's time. And what it would say is that, well, the Triton's time is fast or is slow by X number of seconds. And it would also give you a little button that says, do you wish to synchronize this? And all you got to do is just press yes. The system will then go and grab your computer's clock time and date, and we'll sync it up. And just to be thorough here, Tom is actually at the Spence Space Center in Mississippi here in the U.S. Thank you, Tom.
Okay, going back to that last summary page, if you are connected to a live system, you get a couple of additional options. One is to transfer the settings that you've set up directly to the system, and another one is to deploy the system. At the bottom of that summary, you can also see a number of reminders. So these ones are some of the standard steps that we suggest that people go through before they deploy the system. Zeroing the pressure sensor, always calibrate that internal compass, preferably in the mount, but sometimes that's not always possible, and then making sure that the Triton is actually secure inside the frame. So with all of these steps, you can see how quickly and easily you can go through a deployment of a Triton and actually setting it up, recording waves, recording currents, and have records of the entire thing. When you actually click the deployment button, it goes through also a series of deployment tests, which are very handy because they log some of the performance characteristics of the system before it is deployed. That gives you another record that you can refer to later in the event that there should be a problem, or if you wanted to refer to your settings once again.
Okay, that was the last slide that we would like to present. So at this moment, I just wanted to open up the line for anyone who has any questions. Feel free to type them in. Okay, we have a question here from Mike in Boston. Mike just wanted to know, what are the typical depths where Triton ADVs are typically deployed? Well, Mike, the answer to that is the typical depths are in the range of 10 to 20 meters below the still water line. But they can be deployed as deep as 60 meters. That's the actual maximum limit for the Triton. Now, of course, that the deeper that you install the system, because it's a pressure-based system, the longer the wave periods that you're going to be able to that you're going to be limited to.
Okay, we have another question from Lars on the collection intervals. If we go back to that page, if you set up the system using the standard and sort of automatic settings for how often you're going to collect velocities and waves, it will set it up on a 1-to-1 ratio. However, you always have the option of going to the advanced settings and changing those different collection intervals. So here you have access to the averaging intervals, sampling intervals, and actually the length of the record and how often it's collected. So you have the total control over how those the data collection settings are set. However, if you just want to set it up quickly and have an automatic method of doing it, you can use the standard functions here.
Okay, well, the questions are pouring in. We'll start to just to go through them as best as we can. We have a question from Jay about the calibration procedures. And Jay, I'm assuming that you're mentioning about the compass calibration procedure, as the system itself does never need to be calibrated. The compass calibration is done by, as Matthew suggested, preferably mounting the system in the deployment frame that it will be used, such that you're compensating for any possible magnetic interference that might be present in the frame itself. And that's when you have to do what we like to call the compass dance, where you have to rotate the entire system around at least a couple times while varying the pitch and roll as much as possible. And what that will do is that the compass will be being sampled at this whole time, and will say, okay, well, I am becoming aware of what are the magnetic interferences around me, so I will compensate for them.
One other thing I'd like to add on the calibration is that the ADV itself does not require any calibration, and that compass calibration is typically to compensate for any site variations in the magnetic field.
Correct. I had another question from Kevin on if the Triton is capable to detect if waves are breaking. In a nutshell, I guess no. The Triton will not be able to say whether the waves are actually breaking or not. It will give you the wave height, the period, of course, at that depth. So I guess just some little calculations post-deployment will be able to determine that. But as a direct measure, no, it will not say whether the waves are breaking or not.
Okay, we seem to be getting quite a lot of questions. What we'll do is we'll have a report after this event, and if we can't get through all of the questions now, because they seem to be streaming in very quickly, we can try and answer those questions by phone or email at a later date.
Okay, next question here from Doug in South Carolina. He's asking whether the velocities average over the entire water column, and the answer to that is no, Doug. This is an ADV-based system, meaning it is a point velocity system. So it is not a profiler. We're not looking at the full water column, just at a single point. Okay, the other question here, next question is from Jessica. She's asking, can you deploy the Triton on a mooring? And the answer to that is, it depends. The Triton does have the capability of what we call vector averaging, meaning that it compensates for its own movement. But because we're sampling the data at the rate that we're sampling, the movement of the mooring can't be too fast, for lack of a better term. Really the system that we have for a mooring deployment is called the Argonaut MD, and that one is perfectly capable of handling all mooring situations. Another question here is asking about, I guess, also from Jessica, about how long the system can be deployed on external batteries. It will depend a lot on how the system is set up, of course, how often you request data out of the system. But the typical rule of thumb is that an external battery pack will triple the deployment length that you would normally get without it. Without a battery pack, you tend to get in the range of about 1 to 3 months out of the system. Here in the case of the, as we see on the screen, we were seeing about 19 days worth for power. So should you have a external battery pack attached to the Triton, you'll be talking about tripling that time. So if you are down to measuring waves only once every couple hours, you probably get, I'd say, anywhere between 4 to 5 months out of the system.
Okay, next we have a question from Sandy in Florida on zeroing the pressure sensor. Does that mean just removing the atmospheric pressure? And the answer to that is yes.
At that time?
At that particular time. We can't compensate for changes in the atmospheric pressure during the entire deployment, but at the time of deployment we will offset the atmospheric pressure.
An interesting question here from Mike. Michael about the limitations on the actual mounting of the system. Specifically, what Mike is looking at is will mounting the instrument on a pole that extends above the instrument cause problems? And as long as the pole is outside of the sampling volume by, I would say, in the range of about 10 centimeters or so, then you would be okay. I would typically not suggest mounting a pole that will go through the length of the Triton housing stem all the way into the sampling volume. The chances of actually interfering with the sampling volume itself are small, but you will be really increasing your chances that the pole will cause flow disturbances, which can then flow into the sampling volume.
Okay, we have a question from Robert on integrating the system into a shallow cabled observatory. What you can do in that particular case, the way I understand it, is that you will, if you've got a direct power connection to the system, then the power management is not really important anymore because you've got continuous power. If you're using the internal recorder, then of course that'll be your primary limitation. And based on this deployment, I mean, it can last for an extremely long time. The other option would be to output the data in real time. However, I would still recommend using the internal recorder.
That's actually a good point, because one thing that I just wanted to make clear is that the Triton, for the wave data, will not output the data in real time. The wave data is actually processed post-deployment through our software. So the Triton can deliver the current data, the velocity data that is in real time, but not the wave data, the PUV. But you can have, post-deployment, all of the raw data from the PUV should you like to use, any external programs to process it on your own.
Okay, we have another question on using the Triton-ADV mounted on a boat, trying to measure turbidity plumes. I wouldn't recommend mounting the Triton on the side of a boat. Typically, you're using acoustic Doppler profilers for measuring currents. However, plumes are typically at the surface, and that's a little bit more tricky because of the limitations with profilers related to blanking distance, and they're larger as well. It would be potentially possible to use an instrument such as a PCADP. You would have to keep the boat fairly still. We'll have to get back to Christopher on that one and give him a little bit more information. But I wouldn't recommend using an ADV in that application, purely because it would be very difficult to keep the boat still. But we can discuss that in more detail offline.
Yeah, I concur. Once we know the specific details of the application, then we can figure out things a little bit better. Kevin had a question about how far away from the transducer the point's actually measured. It's a nominal 10 centimeters away from the center of the center transducer. Let me scroll back here through a couple of slides. As you can see, there's probably the best image here that to illustrate this. Where the conversion of these three beams is exactly where the sampling volume is taking place. So you can see from the image right there, it's right at that specific point. So it's nice that it is remote to the system, meaning that the interference that the system itself causes is very, very minimal, if anything at all.
Okay, we've got a question on the actual length of the stem from Jessica. The ADV stem is actually fairly robust. I mean, it's made of stainless steel, and there's a question of whether it's actually ever been broken off, and not to my recollection have we ever had one snapped.
Actually, no, we did. We had one that got caught by a trolling net. I'm trying to recall where it was. I don't think it was here in California. I want to say Florida, but yeah, it got caught by a trolling net, and it just ripped the whole thing apart. So yeah, I mean, you try to it's as robust of a system as you can make it, but if you were to drive your car over it, you certainly would have some damage there. Had another question here from Tom. Let's see here. If I were to deploy a string of ADV, for example, 10 instruments spaced 5 meters apart, how much can we expect battery life to differ between the system, assuming that equal data collection is set up? And if the system's but if the system's depth, the installation depths vary in the order of 5 to 10 meters. Tom, actually, I wouldn't expect it to be much difference at all. Whether the system is deployed at 10 meters or at 20 or at 30 meters, the pressure sensor and the velocity and all of that is going to be working just the same. What's going to have the most effect on battery consumption is how often you ask the system to do its job. Meaning, are you going to record currents and waves once every hour, or once every 15 minutes, or once every 3 hours? That is by far what's going to dictate the power consumption for the system.
We have a question from Lars on, can I have different files with different starting times? Well, the Triton can only record a single file at a particular time, but that single file collects all of the data into a single binary stream. So no, you can't actually have it starting and stopping or having recorded multiple files at different times. It's just a single file started at the deployment time that you set, whether that's right away or in the future, and all data is stored in that single file.
I just had a question here from Don about the side-by-side comparisons between ADV and ADCP wave instruments, and the answer is yes. Actually, there have been several comparisons, and what I can do is we'll have the list of all of your questions being logged, and Don, I'll just send you some references after the presentation.
We have another question from Kevin on sampling rates for the wave measurements, and we can sample waves at frequencies from 1 Hertz to 4 Hertz. Another question that we have from Christopher is on exporting the data that you get from the Triton into ASCII format or CSV, which is a comma separated format. When you actually download the data from the Triton's recorder, it is stored as a binary file. However, if you bring it into the Triton data analysis software, then you can export the data in a variety of different formats containing different parameters. So you can export that in ASCII to Excel, MATLAB, or whatever other applications that you may need.
Yeah, it's been, from the beginning of Son Tek, we've made a point to never withhold any data at all from the customer. So we, from the very first ADV that we've ever made back in 1992 to the latest instrument just shipping off the line right now, we make a point of every single data that our instruments record down to the clock's time is available to the user. Question here from Jessica. Since it is a pressure-based system, how does it differentiate from tide and wave? Well, it's actually fairly straightforward. The frequencies that we're talking about between the tides and the waves are quite different. Whereas tides are going to have periods in the range of several hours, waves are going to have frequencies in the range of actually periods in the range of a few seconds. So typically for tides, what we're using is an average value over the course of the velocity sampling time. So we would average the pressure value over the course of, say, 60 to 100 and 120 seconds, and that will filter out all of the waves and give you a mean water level elevation. And then once you combine that with subsequent measurements, then you can very clearly start picking out the tide. So it really comes down to how often we sample and how much of that data we average. Well, I think we're running out of time here, so I just wanted to thank everyone who has taken out this time. I know it's difficult to set up a whole hour away from your time to be here with us, but we have logged all of your questions. So if you've not had your question answered, just hold on, because we are going to be getting back to all of you with all of your questions. Again, once more, thank you very much.
Thank you.